Bonjour à tous, bienvenue au séminaire du LJLL. Nous avons aujourd'hui le plaisir de recevoir David Poyato, qui est de l'Université de Grenade et qui est venu toute la semaine, que Nastasia et Nathalie notamment, et qui aujourd'hui va nous parler d'un modèle en temps long de reproduction sous l'effet de sélection fortement convexe.
Merci beaucoup. Jouer, David. Merci pour l'introduction et merci aussi pour Anastasia et Nathalie. Alors, moi, je préfère continuer l'exposé en anglais si ça ne vous dérange pas. Un peu plus simple. Alors, je suis en anglais. So, as Emmanuel was saying, today I'm going to talk about this work on the long-time behavior on an equation which arises in quantitative genetics and describes the evolution of a trait in a population that undergoes two phenomena, so Darwinian selection and sexual reproduction. So this is a joint work with Gonzalo Calves, Thomas Leput, and also Filippo Sant'Ambrogio from Lyon that I essentially did in my postdoc in the last years in Lyon before coming back to Granada. And then, let me see what happens. Okay. So essentially, this will be the structure of the talk. I will start with introduction of the model that I'm interested in. It's called the Fisher infinitesimal model. It was proposed by Fisher, actually, not in the form that we will see, but in spirit, it captures the idea proposed by Fisher. And after describing some basic properties of the model and also some literature, I'll be interested in a specific version of it, or a simpler version where we can do some more computations, and then it simplifies a little bit the things. And it's a time discrete model. So we will pass from a time continuous model, which was the original model, to a time discrete model where things are a little bit simpler. And then here, I'll essentially try to illustrate what is the long time behavior that we expect. Okay. And in the third part, which is the main part of the presentation, I will introduce the convergent results that we obtain. These are two types of results. The first one is, so in the first one, we address the long time behavior in a particular case, which is the case of quadratic selection. So here we have the chance to do some more explicit computations. And thanks to that, we can obtain a more general result with regards to the initial datum, which is a generic initial datum. And the second result is the study of the long time behavior in a broader class of selection functions, which will be convex functions, strongly convex functions. But however, we will have to restrict our initial data. If I have time, I'll try to give some sketch of the proof. So let's start by introducing the model, the Fisher infinitesimal model. So in order to, this I don't know why you don't see, but online apparently you see. It must be something from, it's just it's cut okay on there, but then in the screen I see the online people can see. I don't know. Yeah, it must be some issue with the projector. I don't know. So I think that the best is to go to the origin of the model, which appears in a strong debate between people supporting the Mendelian genetics, it's a model in quantitative genetics that I'm going to talk about. On the other hand, people supporting what's called biometricians, who were followers somehow of Francis Galton. So essentially, everybody knows, I guess, Mendelian genetics, where the propagation of traits or a phenotype is understood through the dominant trait, the dominant gene. So after mating, your offspring will have the phenotype which comes from the dominant trait. So there's a predominant gene describing what the resulting trait will be. But however, almost at the same time, Francis Galton was interested in what's called continuous traits. More specifically, he had some tables with that about height of individuals. And he realized that essentially, in a same family, when we observe the trait of the descendant of a same family, essentially, the distribution is normal around the parental mean. And he proposed that this must be a general law. He invented a law which is called the law of ancestral heredity, where he said that, okay, both the father and the mother, both ancestors should contribute equally to the final trait of the individual. Of course, this is not what Mendel had in mind, because there's a dominant trait and gene, and then this is the gene that is going to describe the final trait in our individual, right? So in the middle of this debate, there was Fisher who appeared to try to put both point of views in agreement. And more specifically, he observed there are some traits which are called polygenic traits, and they are affected not only by one gene, but several genes, which have each of them a small quantitative additive effect on the final trait of your descendants. And he observed that precisely this could explain that the offsprings are normally distributed around the parental mean. So somehow we depart from Mendelian genetics, but the final result is that you can describe continuous traits which are distributed normally around the parental mean. And essentially, in a very schematic way, this is what Fisher proposed. If you have parents with traits X1 and X2, the resulting trait for children is essentially the mean plus a small deviation, which is distributed normally with a given and fixed variance, which doesn't depend on the generation, on the parental trait, anything is just constant. It's called the segregation variance. Okay, this model was later justified with a statistical method by Nick Barton and some other collaborators. And then we have this point of view is really justified using central limit theorems, departing from model from Mendelian genetics. Okay, so in a sense, this can be explained. But of course, we're interested in equations that describe the dynamics. So how can we see at the evolution of the traits in a population undergoing sexual reproduction through this description given by Fisher? Selection. So in general, we will be interested in model of this type. So it's an integral differential equation which contains two terms. There's this term in blue, we represent selection. So it's a multiplicative operator by a function n, which is called the selection or mortality function, and depend on the traits. And then there are some traits that are more likely to survive than others. It depends just on the traits. So when we have the minimum of the selection function, we have the more chances to survive selection. And on the other hand, we have a growth term, which is described in terms of what's called the Fisher infinitesimal operator, and describes the sexual reproduction. So the continuous description of the previous statement by Fisher is recasted in this form. So essentially here we still see that after mating of two agents or of two individuals with trait X1 and X2, our descendants will be distributed with traits X, which are distributed normally around the parental mean. Here, G0 sigma S squared is just the Gaussian center at the origin with variance equals to the segregation variance. Okay, so this is the translation into math of what Fisher proposed. Here I put some references, but I won't describe them at this moment. I will describe in a minute. Some people who already work on it. But before doing that, let's go and see some properties of the sexual reproduction operator, Fisher infinitesimal operator. So this operator has some properties, basic properties like it preserves the mass. It means that the integral of B of f is equal to the integral of f. Of course, this doesn't mean that the mass is preserved in the system, but it just means you have selection here, and you try to compute the growth of the mass. It grows exponentially because the B of f has the same mass as f, right? So mass grows exponentially. This is a Malthusian behavior on the mass, right? And another property is that through this scaling here, the operator becomes one homogeneous, despite the fact that the operator is nonlinear. Okay. The operator also preserves the mean or the center of mass, say, and its translation invariant. Of course, there's no if there's no selection acting on the system, there's just reproduction. There's no predominant trait. There's no trait which plays a specific role, and this plays we can make shifts in the trait and get the same distribution of descendants. No? And then the most interesting property was found later by Gael Raoul in 2017. It's inspired in some inequality proposed by that for the Boltzmann equation, actually. Although here we have an operator that looks a little bit like Boltzmann collision operator, but it's non-conservative, but things change a lot. But there's still some property found by Gael. More specifically, we have two distribution with the center of mass, and we compute the distribution of their descendants. The quadratic versus time distance is contractive, contrasts with a specific rate. which is 1 over square root of 2. And this is very important. Well, here I'm using the quadratic Wasserstein distance. For those who are not very familiar, it's a transport distance that arises in the mathematical theory of optimal transport and has this expression. So then how can we find some preliminary result on the long time behavior of the system? Let's focus on the case without selection. So we kill the selection term. The mortality function is a 0. There's no selection. And of course, if we compute IT, it's going to be the total mass of the system. And we normalize the profile so that we keep them probability measures. Actually, the nice thing is that we can split the system in an independent system for the mass and the normalized profiles. So the mass, as I said before, it grows exponentially. We have this equation. And the profiles verify this modified equation. But then what is interesting is that if we depart from initial data, which have the same center of mass, and the center of mass is going to be preserved by the dynamics thanks to the fact that we have an operator which preserves the center of mass, then we may compare, or we may use the previous contraction argument for the Wasserstein distance, and very quickly we arrive at this strong contraction on time of any given two solutions to the system. So there's a strong contraction in the quadratic Wasserstein distance with respect to the initial datum, where the rate is precisely the 1 over 2 that appeared in the contraction found by Raoul. No? So this characterizes completely the dynamics in the case without selection. Okay. So in particular, what are the consequences of this? So the first thing is, by inspection, we immediately see that there's an equilibrium here. It's a Gaussian with a variance which is twice the segregation variance. Okay, this we can compute by hand because B is explicit. Just essentially it's a nonlinear way of making convolutions with the Gaussian. So we can check this. What we indeed have is that this is the only equilibrium because we have strong contraction for any couple of solutions to the equation. And also, if we fix N2 to be precisely the equilibrium, we have a contraction estimate or long convergence estimate to the equilibrium, right? Which converges exponentially fast to the Gaussian profile with explicit convergence rates. But of course, this is in the case where there's no selection, where we can use this nice contraction property of the operator B. However, what happens if we have selection? Do we have chances to apply optimal transport arguments to find an alternative contraction estimate that help us and we get a problem solved? And the answer is no, because of a structural problem that we have with multiplicative operators. So selection is a multiplicative operator. And what they claim is that multiplicative operators are not Lipschitz continuous. So if they are not Lipschitz continuous, we don't have any chance to have them contractive in Wasserstein spaces, the quadratic Wasserstein distance in particular. And a very simple example is the following. So let's take a function m, which is, for instance, imagine it's just a parabola. And then we take initial measures, which is going to be, the first one is an atomic measure, which has two atoms at minus h and h with the same mass. And the second distribution is just a small shift to the right of the first one. So the quadratic Wasserstein distance between the two is just epsilon, because I made a small shift to the right of the initial distribution. And now what I'm going to do is to apply the multiplicative operator to both of them. This I call F1 bar, F2 bar, multiplied by n. And since they are not probabilities, and then I cannot measure using quadratic Wasserstein distance, let's for the moment normalize by the total mass. Okay, so if m is radially symmetric, like in the parabola, in the case of the F1 bar, so the image of F1 is again F1, because F1 was symmetric and then it's symmetric. So it stays invariant under this operator. However, if I have F2, which was not symmetric, and I apply the operator F2, I'm going to charge more the Dirac mass in the rights. And then if I want to compare the quadratic Wasserstein distance between these two, I will have to take a small portion of the mass at the Dirac mass minus h, actually a portion of the mass of size epsilon, move it to the right along a distance of order 1 to h minus epsilon, and this, if we make the computations, contributes with the square root of epsilon. But the square root of epsilon is the square root of the quadratic Wasserstein distance of the initial measure before applying operator, multiplicative operator. So this tells me that I don't have any chance in principle to to have even lattice continuity of this type of operators. We have to probably find an alternative. So very quickly, what has been done in the literature. So this model has been already studied in particular by Sepidemi, Raimi, and Garraul, where they study that essentially it's the same model, but they also include, well, the model is also structured by space. So there's dependency on positions. And what they study here is the large frequency limit. It means that we put a small parameter, a large parameter, sorry, in front of reproduction term. And then we try to see what happens in the limits. So if we put a small parameter in front of the, sorry, a big parameter in front of the reproduction, it is essentially the same as killing the selection term. So we are working in a regime with weak selection. And then this is what they essentially exploited. They use again that we are in a perturbative regime of the case without selection, where we can use this contraction estimate, the quadratic versus time distance. So essentially this was the idea to understand the limits. Later, again, Raul considered a similar model, but where selection appears inside the operator B as a multiplicative operator again, in the reproduction, the fecundity rates. It's very similar. So what he did is that if we have a small perturbation of the case without selection, again, we can characterize the dynamics. So we have a uniqueness of a equilibrium, and we have a contraction to such an equilibrium, at least locally, when we start with initial data close enough to the equilibrium. Right? Again, this is a perturbative regime of the case without selection. What has been done in the case with big selection? So we have some words, but of completely different nature. And in particular, Vincent Calvez, Jimmy Garnier, and Florian Patou, they have some works where they study the limit of a small segregation variance. So this parameter sigma s, the segregation variance, is taken very small. And they try to characterize the asymptotic dynamics in this regime. But it's a completely different question. They don't ask about long time dynamics. Okay. So let's try to simplify a little bit the model, because the initial model, time continuous model, is too complex. And in order to do so, I propose some time discretization. So I remind you that the equation was of this shape, and then we can look at it as a linear equation with a perturbation term. We use Duhamel. We integrate among 2 times Tn and Tn plus 1, which are going to describe a discretization of my time, my space of times, no? And then, just using left rectangle rule, we immediately obtain a discretized version of the model, no? Which could be this one, where due to the Duhamel formula, we have this exponential of minus m. So the dependency on the selection becomes now this e to the power minus m. So essentially here, what we have is the individuals of the previous generation which have survived after selection. In the second term, we have the offspring of the previous generation which have survived after the effect of the selection. Okay, this is essentially what we have, and this e to the power minus m, since m is typically non-negative, is always a quantity which is smaller than 1. It could be interpreted as a probability of survival. So when m is smaller, e to the minus m is bigger, and we have more probabilities to survive. No, so this model is still complicated, and for the moment, let's consider the following model. Actually, we will focus on the following one. We are going to assume that we are going to kill all the individuals in the previous generations, and this is a strong simplification, but there are some systems in which this happens. There are some systems of, usually they are insects that reproduce only once by season. When they reproduce, they die, and there's only their descendants which are going to stay. So this could be one model. And if we look at the shape of the model, it's just an iterative model. No? So we have an operator acting on Fn minus 1, which is going to describe the distribution of my traits in the next generation n, right? So in principle, we may represent as follows. So Fn is going to be T of Fn minus 1, where T is the combination of a multiplicative operator and the Fisher infinitesimal model. Still, we have selection acting as a multiplicative operator. So we have the same problems as before with regards to the quadratic versus time distance. We don't have any chance to have contraction in the quadratic versus time distance. So this is the model as it is done usually in other equations structured by by some variable, age, trait, or whatever, let's try to look at equations which have the following shape. So we propose that they are, so we decouple the dynamics of the mass with regards to the dynamics of the profile. So the profile we are going to fix, and mass is going to grow as a power of lambda. So lambda and f are unknowns. And if you plug this in the problem that I'm going to call P, the problem that we arrive at this type of generalized or nonlinear eigenproblem because the operator P is nonlinear. So when we look at this reminds us a little bit to why not applying probably a Crane-Rootman theorem, as usually is done in equations which are structured by some variable. No? Of course, a first obstruction is that the operator P is nonlinear. Okay, there are some extensions of the Crane-Rootman theorem for operators T which are nonlinear, but all of them, they need that the operator is one homogeneous, and this we have, but it is also monotone. An operator, due to the structure of operator B, more precisely because we are dividing or normalizing by the mass, is non-monotone. So we don't have any chance to apply classical arguments to characterize the long-time dynamics. So let's see what can we do. Essentially, these are the two questions that we will focus on the talk. So first, does the eigenproblem has a limit solution, lambda f? And is this lambda f going to characterize the long-time dynamics of the general problem P? Essentially, we expect that the normalized profile are going to converge to the profile f. And somehow lambda is recovered as a limit of something that has to do with mass. This is the question. Okay, so before stating any mathematical result or argument, let's just look at some clues that are going to give some information on what do we expect as a limit of the problem P, long-time behavior of problem P. And let's focus this first clue on a special solution in the case of quadratic selection. So let's take as a selection function a quadratic function. Okay, so we have a quadratic function, and since the operator T is a combination of multiplying by e to the power minus m, which is a Gaussian now, thanks to this quadratic choice, no? And convolution with Gaussians, which are appear in the definition of operator B, we see immediately that Gaussians are the class of solution that is stable. So if we depart from an initial datum which is Gaussian and we apply operator T, we recover another Gaussian with different mass, different mean, different variances, but still Gaussian. And we can actually find recurrences. This is just a explicit and very stupid computation on how the mass behaves. So this is a recurrent equation on the mass. This is a recurrent equation on the means of my Gaussian solutions. And this is a recurrent equation on the variances. Okay, everything is explicit. This is a special class of solution to the evolution problem P, but we can do the same for the eigenproblem. In the eigenproblem, we can try to study Gaussian solutions, and there's only one Gaussian solution whose eigenvalue lambda is given explicitly as it is appear here, and the variance is solving this implicit equation. So there's only one possible root of this equation we can solve. So we have Gaussian solution to the evolution problem and Gaussian solutions to the eigenproblem. And we try to compare if there's really convergence. And this is explicit because we only have to see the long-time dynamics of these quantities we described. And it's easy. Actually, we can see that sigma n converges to the variance associated to the Gaussian solution or the eigenproblem. We can do this, and we even have explicit rates. The mean, so we look at this, and then we see that the sequences of means are going to converge to 0. And the mass, if we look at the dynamics of the mass, is going to converge actually to the eigenvalue. And we have explicit rates. On the one hand, I realize that the eigenvalue is recovered as the limit of the rate of growth of mass. So the mass of generation n over the mass of generation n minus 1 with explicit rates. This is the rate in terms of the parameter alpha, in terms of the variance more explicitly. And if we want to compare the convergence of the normalized profile, so now I divide by the total mass, so there's only the normalized Gaussian that remains, and I want to find if this converges to the eigenfunction. So this we can do again. In particular, here I use the relative entropy as quantity to quantify the convergence, or also called the Liber divergence. We obtain explicit convergence rates. So in general, what we expect is that the normalized profiles are going to converge to the Gaussian solution, and the rate of growth of mass is going to converge to the eigenvalue. This is explicit for Gaussian solution, but we don't know if this is also true for a generic initial. Okay. I didn't say anything about the conversion rates, but of course, this quantity that appears here, this factor K alpha is smaller than 1, and we can plot it. So it's smaller than 1 as a function of alpha. It's only that it degenerates at alpha equals 0. When we have alpha equals 0, we obtain the conversion rate is exactly 1. And then there's no convergence, but this is natural because the Gaussian solution is centered at the Gaussian solution to the game problem is centered at the origin. And if we don't have selection, this would correspond to alpha equals 0. There's no reason why the means of my initial distribution should move and travel toward the origin, because there's no effect of selection. Okay, and there's actually conservation of the center of mass, right? So this estimate is only meaningful, also only gives some information for positive alpha, but also we have all the information we wanted for alpha equals 0, no? So our goal is alpha positive. Okay, so Gaussian solutions converge to the Gaussian eigenfunction. This we know, and is it something very particular of having started with Gaussian initial datum? So if we do some numerical simulations here, for instance, I started with this step function. It's not a Gaussian solution, of course. We see how along different generations there's this Gaussian that is formed, and then the Gaussian is going to travel very slowly towards the origin, so until it gets centered in the origin, and we again recover convergence of the normalized profiles to the Gaussian eigenfunction. And essentially, we also look at the rate of growth of the mass. It also converges to the asymptotic limit is precisely the eigenfunction, the eigenvalue, sorry. So we expect that the same should hold for any generic initial datum. It's not a particular behavior of Gaussian solutions. In fact, we even can compare the numerical rates of the previous solution starting at generic initial data with the rates of convergence that we obtained for Gaussian solutions, and we see that they are sharp. The diagram that is just telling that. So we, in general, we believe that the convergence rates for generic initial data should be exactly the ones found in the case of Gaussian solutions. At least this is what the numerical simulations tell us. So let's start with the first mathematical result in this direction. So do we have any chance to characterize the behavior of the problem, starting with generic initial data, for instance, in the case of quadratic selection? So this is the first result. In this result, let's focus on, again, back in the case of quadratic selection. Our selection is a quadratic function. And what we obtain mathematically is the same as we saw before. So the normalized profiles are going to converge exactly the same convergence rates to the Gaussian eigenfunction, and the rate of growth of mass is going to relax also to the eigenfunction, eigenvalue, sorry. Here we have the optimal rates with regards to the convergence of the normalized profiles. However, mathematically we couldn't get the sharp convergence rates with regards to the convergence of the rate of growth of mass, and it's because of a tiny step of the proof, but probably it can be, some of you know how to solve it quickly. So essentially, this is the representation of the rate of growth, the rate of convergence as a function of alpha, which we obtain in the class of Gaussian solutions, and apparently is going to be the sharp rate. If we plot, so in red, the rate of convergence for the normalized profiles, they agree completely. However, we have this small mismatch with the rate of growth that mathematically or theoretically we obtain for the rate of growth of mass. And we will see in a minute why this appears. Okay, so essentially we have optimal rates, a modular tiny thing that we have still to solve. So in particular, this tells us that the only solution to the game problem is the Gaussian solution that we built by hand. Why this? Okay, so if we depart from any other solution to the game problem, lambda f, we can build a solution to the to the evolution problem, lambda n times f. This is going to describe a solution to the game problem, and then we compare it with the Gaussian eigenfunction using this theorem, and of course we obtain that the eigenfunction has to be exactly the Gaussian eigenfunction, and then the associated eigenvalue has to also agree with the eigenvalue associated to the Gaussian eigenfunction, right? So there's only one solution to the eigen problem, which is in this case the Gaussian solution. This result, I don't want to enter into the detail of the proof because it's particular of the case of quadratic selection. But essentially, if you want me to give very quickly some ideas. So this is our problem, it's an iteration problem. Sorry, this is mistake. Here should be fn minus 1. So our question is, do we have a way to see that by iterating the operator t several times, many times, it forgets somehow the initial data, and then we observe convergence to the Gaussian. This is sort of a godicity property of convergence to the equilibrium, actually. So essentially, if we iterate n times, since any time we are applying the operator t, we have two integrals. In the operator t iterated at n times, we have 2 to the power n integrals. So this is an operator, an integral operator in dimension 2 to the power n. So integrals in r to the power 2 to the power n. So a lot of integrals. And but however, all we are doing is convolutions with a Gaussian, multiplication by a Gaussian, because we are using quadratic selection. So there may be a way to rearrange the terms, even though we have a huge integral with 2 to the power n terms, so that we see more specifically the dependency on the initial datum. So this can be done. There are some change of variables that one can do. And what we observe is that the fnx, so the solution at time, the generation n, modulus a multiplicative constant, I'm not going to write, it's not important in the following, is essentially nth and tilde. These are explicit Gaussians that are going to check that this converges to the right Gaussian eigenfunction. Times some remainder, which is this operator epsilon n acting on a normalization of f0. So we have to normalize appropriately of f0. But it's an operator that is only depending on the, and since this part is already converging to the appropriate Gaussian, we expect that this somehow forgets the initial datum. So more specifically, or more easily, we have an alternative way of looking at it is we take the log of this and we differentiate. If we take the log of it and we differentiate, the multiplicative constant is not going to play any role, and we arrive at this explicit equation, where I was saying that this converges already to the appropriate thing, but there's a remainder that we expect that is going to converge to 0. And if we do explicit computations, so here is the high dimensional integral that appears, we observe that there's a factor that appears once it differentiates. It's a sequence kn, which converges to 0, times a sum over a set of size to the power n. Essentially, what I'm doing here is I'm departing from x, and I'm building the tree of the ancestors. So this is a binary tree, okay? You can continue it. And in the operator epsilon and f0, more specifically in the gradient of its log, what you see is that there's only the dependency on the last layer. The last layer means the layer at the height n, which contains 2 to the power n terms. And then if I have some estimate on the gradient of the log of f0, this is some initial assumption. Namely, if I have that this is bounded, the gradient of the log of the f0 bar is bounded, here I have kappa n, and here I have 2 to the power n terms. And then essentially what I will have is that this remainder could be bounded by 2 to the power n times kappa n times the L infinity norm of these initial objects. And if we look more specifically at the behavior of this is going to converge to 0, precisely when alpha is positive. So this is a very naive idea, but of course here we are imposing a very strong assumption. We are restricting to initial data so that this quantity is finite. And typically, if you have a Gaussian initial datum and you take the log of it and you differentiate once, this is something that grows linearly. Generally, we don't have that this is bounded. We cannot. We can't use this stupid idea, no. So we have to work a little more, and this is essentially what we did in this work. We have to work and control actually some moments that are gonna control the tails that appears here, the linear terms, terms that grow linearly at infinity. But it's doable. We do this, and we arrive to the result. However, here I would like to talk about this second result. This is a result again with Vincent Calves and in this case with Filippo Sant'Ambrogio on the general convergence to the general long-time behavior of the problem for a broader class of selection functions. Instead of restricting to something that is a quadratic function, we have something more general. So let's first introduce what's the more general assumption. So we are going to consider some function which is alpha convex. This means that the second derivative grows, it's just lower bounded by a positive quantity. so stronger than convex, in particular quadratic function like here. More particularly, if you have a quadratic function, you add any convex function, you have this is actually the definition of an alpha convex function. Okay, it's something that grows above something quadratic, in particular contain quadratic functions. And so here I'm not going to introduce the final result. What I'm going to introduce is the main lemma that lead us to the long time behavior. And you will see that it's slightly different to the previous statement that will yield as a consequence the completely analog version of the previous theorem in the case of quadratic selection. The reason why I introduce it in this way is because we can see actually the method. We can see actually which is an appropriate norm and space where we compute things. So first of all, what we proved is that the generalized eigenproblem, so the nonlinear eigenproblem, has a strongly log concave solution. So a strongly log concave solution is a pair where the profile is a strong log concave function, namely is the negative exponential of a strongly convex function. The modulus of log concavity of the eigenfunction is explicit. It's given in terms of alpha. You only have to solve this implicit equation and you get it. Like, okay. We don't know that this solution, log concave solution to the eigenproblem is unique, but at least we can ensure that it's unique locally. So among all other solutions, so that this quantity that is very similar to the previous one, the log derivative of this f over the strongly log concave solution is bounded. Okay. So first we prove the existence of a strongly log concave solution to the eigenproblem, that is the analog of the Gaussian solution in the quadratic case. Okay. Particular in the quadratic case, we do have a strongly log concave solution, which is the Gaussian eigenfunction. Any Gaussian is a strongly log concave function. It's a negative exponential of a strongly log concave function, a quadratic function. And second, how about the contractions or the long time behavior? So again, we have an hypothesis that in this case we were not able to remove, at least for the moment. So let's take an initial datum and let's assume that this quantity, so when you take the log derivative of f0 over the strongly log concave solution to the nonlinear eigenproblem, this is bounded. So we are restricting the initial data. And in particular, if I come back to the quadratic case, since f was a Gaussian function, and if I look at f0, which are Gaussians, the restriction is more specific. I'm taking Gaussian with the same variance. Okay, so it's quite strong, but still we don't have any information about where their center of mass is located. Okay, and then what we proved is that there's a quantity which we call the L infinity Fisher information, which is contractive. So when I compute the distance between the normalized profile to the strongly log concave function, it is contractive with respect to the initial value with a explicit rate, which is again exactly the same rate as before, which by the way is the sharp rate for numerical simulations and also for the Gaussian solutions. Okay, so what's important here is that there's this object appearing, which we call the L infinity Fisher information, and the reason why we call it the L infinity Fisher information is because there's a L2 Fisher information, the usual Fisher information. When instead of taking L infinity norms, we are taking a weighted L2 norm with respect to P. Here we are replacing the L2 norm by L infinity norm. Okay, that's why we call it L infinity Fisher information. But this quantity is contractive. And of course, if we have this, we have a lot of information already about the final long time behavior. So we have several consequences. So for a moment, I will skip the proof of it. I don't know how I'm on time. I have to check because I have to run a little bit. But let's assume that this main lemma holds, and then let's have some consequences, immediate consequences about the long time behavior, which are comparable to the quadratic case. So first of all, it's clear that since f is strongly log concave, the relative entropy can be bounded by the quadratic Fisher information, the Fisher information, the usual Fisher information. And this is called the log-Sobolev inequality, which holds because f is strongly log concave. And of course, two norms can be bounded by L infinity norm. So I can bound the L2 Fisher information by the L infinity Fisher information. But this, I'm saying that is contractive. So then I can translate this information into a quantity which we are closer, which is the relative entropy. So the relative entropy converges to 0, and we have the explicit rates. There we have a square, which we didn't have here. So this completes the sharp rates that we found on the case of quadratic selection function. So immediately from the contraction of the Fisher information, we have that the relative entropy relaxes to 0. And we have some information also on the long time behavior of the rate of growth of mass. So I would like to say again that the rate of growth of mass is going to converge to the eigenvalue. So if we write explicitly this, we find this expression where phi is explicit functions. Actually, is given in terms of the Gaussian and the selection function. It's explicit, but everything we need to know is that it is a continuous and bounded function. So here I can use simply Heller inequality. I bound this in L infinity and I bound this in L1. But if I bound this in L1, now I can use Pinsker inequality, which bounds both the L1 norm by the square root of the relative entropy. And we all know that the relative entropy is a quantity which is tensorized. So this is just twice the relative entropy between the object, the non-tensorized object. And then we also have the convergence of the rate of growth of mass to the right thing. But it is due to the fact that we are using Pinsker inequality that we lose a little bit in the convergence rates. So here is where the non-sharp rate appears. It's because of there's a square root of the relative entropy that appears here in front when we use Pinsker inequality. So maybe working with some alternative versions of Pinsker inequality with weights, we may arrive to a way to get rid of the loss of sub-convergence rates, but I'm not sure. Or maybe we have to work a little more and find some hidden cancellations that we don't see, of course, if we apply Pinsker inequality. But of course, we have what's called asynchronous exponential growth. So we have that the normalized profiles converge to the right thing, so the extremely low concave function, and the rate of growth of mass also relaxes to the eigenfunction, to the eigenvalue. It's a consequence. So all we have to do is to focus on the proof of the lemma. So first, existence of extremely low concave solution to problem E, the eigenproblem, and later this nice contraction property of the infinity Fisher information. So yeah, here I think I'm not going to talk much about it, but this work is somehow related to some very well-known approach, which is the Bakery-Emery approach for Fokker-Planck equation. So here is the Fokker-Planck equation, and essentially what Bakery-Emery did is, if we take the entropy, the Boltzmann entropy, and we compare F with the equilibrium to this equation, which is e to the power minus b, the potential. If we differentiate here, we obtain the dissipation, which I call D. And the idea by Bakery-Emery is to prove that this dissipation decays. In the case of the Fokker-Planck equation, the dissipation is the L2 Fisher information, the L2 version. And then Bakery-Emery proved that this contracts if we have that the potential V is convex. Okay, so under some convexity property of V, or in other words, some strongly low concave property on F, we have the contraction of the L2 Fisher information, which here is the dissipation. And then this dissipation decreases exponentially fast, and if we integrate with respect to time, actually this tells some information with respect to the relative entropy. So the relative entropy also decays exponentially fast. So we have exponential convergence to the stationary measure in the Fokker-Planck equation. So here the idea is to find contraction of the dissipation. The dissipation here has a specific expression. It's the L2 Fisher information. What we are doing is somehow not very far from here. We are proving that an alternative object, which is our L infinity Fisher information, is contractive. Under which assumptions? Well, very similar ones. The equilibrium is strongly low concave. Okay, so although this equation is our system is not conservative compared to the Fokker-Planck equation it is, there are some analogies. So in the little time I have, let me focus. I won't have time to prove to show the existence of strongly low concave solutions to the game problem. Let's admit this for a moment, and let's go directly to the basic idea of the proof, which I want to be very quick. So let's focus on the contraction property or the L infinity Fisher information. So the first idea is, okay, so we define this quantity, which is, I take the solution and I normalize by the lambda to the power n times f, where lambda and f are the solution, the strongly low concave solution to the game problem. And then we see that there's this alternative equation on UN. So UN essentially is defined from the previous generation through something that I call here P, and is playing the role of transition probability. So here I'm saying the probability, which is the probability of having a descendant with trait X if I have two ancestors with the probability X1 and X2. And this P is explicit. This modulus and constant, the negative exponential of some potential, which depend on X, X1, and X2. And it's given explicitly here. This V is not explicit, it's the potential associated to the strongly low solution. It's the only non-explicit thing, which would be explicit actually in the quadratic case, but not here, because we don't have explicit solution to the strongly nonlinear problem. No? So we have this structure, and what is interesting is that we have this inequality of this result. As far as we know, it's new and probably of interest on its own, and we call it the infinity version of Kantorovich duality. Why? Because there's a classical one, which is the L1 version of the duality. Everybody knows that if we have some u0, some function, and iterate with respect to some measure mu1, and I make the same computation with respect to a second measure mu2, these in absolute values can be bounded by the ellipsis constant of the function u0 times the w1 versus time. This is classical, and it's actually a consequence of Kantorovich duality. So what we have here is an alternative version. So u1 and u2 is just making these integrals with respect to different measure, namely the measure p in variable x1 and x2 with the associated parameter x, and the same measure variable x1 and x2 but with an alternative parameter x tilde. Okay, and what we see is that this can be bounded. The log of this, sorry, the log of the difference of the two things. So there's a nonlinear thing instead of just computing this integral and taking a nonlinear function of it. This is the log. This quantity is bounded by the L infinity norm of the log derivative times a quantity which is now the W infinity versus time distance. This small one here actually is representing that as norm in the Euclidean space R2, because I have two variables, x1 and x2. I'm picking the small L1 norm. It's just the sum of the two components. It's nothing important. But it's that W infinity versus time distance. So this can be regarded as a nonlinear version or L infinity version actually of the classical Kantorovich duality. It's not a particular thing. There's a full hierarchy of inequalities which interpolate the p equals 1 with the p equals infinity. But in particular, we have this control, and then anything we have to do is to show that this contracts with respect to x. So this is, I'm not going to skip this. So this is the first step of the proof. We show that the L infinity versus time distance is contracted with respect to the parameter x with explicit contraction parameter, which is back here k alpha, the sharp rate. I'm going to skip the proof, but the proof is very interesting if somebody wants to see. It is based on a Caffarelli maximum principle. So here we use, since we are working with transport distance, I use the Brenier map. The Brenier maps of the Monge-Ampère equation, and then in the Monge-Ampère equation there are some nice maximum principles that here we have to adapt a little bit, but you can work with it and obtain nice estimates on L infinity versus time distance, even though the probability P is not explicit. But everything we need to know is that the potential V appearing there was strongly convex. So we have that. And then how can we close the argument? So finally, to close the argument, we come back here, the nice inequality. And since this is bounded by k alpha times the distance between x and x prime, essentially what we have is that the log derivative of u1, which is the first iteration, is bounded by the log derivative of the initial u0 times the contraction factor. And then I'm done. I'm finished. Okay. Of course, there are a lot of issues hidden here that I'm not going to describe, in particular the maximum principle in the full space, because we are working in R2, our P is defined for x1 and x2 living in the full space, is not clear because when you apply maximum principle, the maximum has to be attained. In non-compact domain, you cannot do that. But there's an alternative. What we did is to essentially cut off the problem into squares and pass to the limit, and this works. So there's this nice thing. This is the result that we did with the Filippo Sant'Ambrogio that's also interesting to him actually for different issues. We have a control on the infinity versus time distance of strongly log concave potentials on squares. And the square is a bad domain because when you try to use the regularity theory of Monge-Ampère equation, you know that there's elliptic regularity if the domain you are working in is strongly convex. But square, which is the domain we use in the discretization, sorry, in the cutoff, is not strongly convex domain, and we have to work a little more because we didn't have in principle the full elliptic regularity we need, so not maximum principle, but it's doable. Interesting that it's precisely this contraction property that is also going to help us. This I skip, but the proof of the existence of a strongly log concave solution to the Eigen problem is also based on this very same contraction property on squares. Okay, so since it's technical, I think I'm going to skip all this. here I have some conclusions. So of course, the nice thing is that we can work on non-perturbative readings of the case without selection. Our selections are big. The first work is a parabola, and in the second work we have any strongly convex function. And we have optimal, say, convergence rates to equilibrium. There's only a small mismatch, as I told you before, on the rate of growth of mass. The nice thing of the quadratic case, or of the first result, is that we have generic initial data. The bad thing of the second result for strongly convex selection is that we don't have the freedom on the initial data, but still we captures the optimal rates. Some clear perspectives, of course, trying to tackle the case of generic initial data with strongly convex selection is trying to consider overlapping generation. So at the very beginning, when I kill one of the two terms in the discretization, why not keeping that term? That's complicated things a lot. So what happens if we don't have a non-convex selection? This is a very interesting question, I think. So let me just finish with this picture, probably, where we see that this is the selection function. This is not strongly convex. It's not even convex. It has two minima, two different points. And if we do numerical simulation, so here I started with a step function, it's more square. We see that immediately the first generation, we find this looks like a Gaussian, but it's not really a Gaussian. There is form, and for long enough generation, here I plot n equals 40, we have convergence to this profile. However, this is very sensitive to the initial data we take. If we switch or we center completely the square at the origin, because here I have a symmetric function with respect to the origin, we see a phenomenon of segregation. So we have that part of the mass goes to the left, part of the mass goes to the right, and there's a final equilibrium that appears, which is different from the first one, which has mass locally around the two minima of the selection function. But then if we switch more to the right, and then we are again back in symmetric setting, we see that all the mass travels around the second minimum of the selection function. And of course, our method is not going to work the same way, because here we have several equilibria, right? So this would be a very nice situation to work in, because in particular, our methods are not clear if they will work or if they provide something. So let me stop here, and I thank you your attention.
We begin with the convergence with non-control with a certain distance.
Yes.
But is it known that they converge strongly in L1?
Is it known that they converge strongly in L1?
Convergence to the steady state in L1. I was thinking at the very beginning.
Yeah, but this is a consequence of functional inequalities, no? Because at the end you can compare W2 versus time distance with L1.
No, if you converge with a certain distance, you converge weakly. You don't converge.
But you what you have is that your final equilibrium is strongly log concave, no?
Okay, so what? So the limit is in L1. Why do you think it's L1 convergence?
Sorry, I didn't understand. Why do I claim that there should be convergence in L1 in the case without selection? I don't know, and I didn't say that actually. I don't know. Let me think a little bit, but because you like to compare with this, that in particular, yeah, it's converging L1, no?
Yes, because at the end, everything is strong convergence. Whenever you speak with relative entropy, then you are in strong convergence.
Yes, there's strong convergence.
I wonder whether there is a direct proof of convergence. Again,
well, I have to look at it. I didn't pay attention exactly to whether it's possible to get strong norms in the convergence of because, but to my knowledge, it's not written at least, but it makes sense that it is feasible. I don't know. Here I focus on the case with selection and yes, by the case I work in, but you're right that why not having stronger convergence in the case without selection, probably something that we can do or one can do, not very complicated. I don't know. I can check later and try to answer. Because you like to see the contraction at the level of a quantity which is not contraction in W2, the Tanaka inequality, but something that is
contraction, I would say, if it wasn't true, it should be known. So that it's not contraction, but it could converge strongly.
Yeah. So what I would do is to try to see if this Bailey-Emery approach works. But of course, when you try to do this, well, I have to think, but well, thank you.
Y a-t-il d'autres questions? Y a-t-il des questions à distance? Ok, s'il n'y a pas d'autres questions, merci encore, David.